Hey there, everybody. I got 6:30, so I'm going to get underway. So the plan tonight, as you see, I've got some ideas that we've been exploring here within Chapter 5. So my plan this evening is to revisit just a few of these since we've been away from a lecture for a week, review a few of the ideas, and then add in some new ones in 5.7 and 5.8. I think that'll take probably towards the first half of class, and then move a little bit to get a head start on some ideas that we're going to find in Chapter 6. So I'd say half the class is finishing up Chapter 5, and then half the class is new stuff from Chapter 6. Now, before we get rolling on that, I want to share with you what I think is our plan as we head towards our second exam. So here we are on Thursday. You'll notice within Mastering Chemistry, the top there, that's the calendar for that. There's different assignments pertaining to Chapter 5. These are ones that many of you have already been working on, and many of you have also completed them. These are ones that are pertaining to Chapter 5 that we had over the last week or so that I bumped ahead. So do your best to work on those, because we have our exam coming up, and I know that Chapter 5 is going to be important content. On the bottom here, I show the portions within perusal that we still have coming up. So this evening, we're going to be working again on ideas from Chapter 5, start Chapter 6. And then next week on Tuesday and Thursday, those are more opportunities to work on stuff from Chapter 6. So I think I got a pretty good plan as we move towards the exam. A couple features I want to add to this. We're going to have practice tests available. I'd suggest, and I'll be introducing the idea probably towards the end of next week. That's where it would be a good time to begin using those as a particular resource. As I was thinking and bringing together the ideas as well, I also thought it might be helpful if I can provide you with a video that provides a review of some ideas from Chapter 4 and 5. So I'm making that tonight, I'm making it tomorrow. It should be in perusal by Saturday. I'll let you know when that video becomes available. I'll send everybody an email. Now, if I'm making that particular content, I think it's going to be valuable for you to use to bring together your ideas before you take the practice exams. So I decided I'm going to make it an extra credit assignment within perusal. Now I've got to give a due date on that, so I'm going to list it for next Tuesday. I might be able to adjust that, switch it. I mean, class is going to be more important than doing that particular assignment, but I got to put it somewhere in perusal. So that's going to be my plan. When I put it into perusal the first time, I'll let you know, I'll send you a message. But I think it's going to be a really helpful resource as you bring together your ideas here for Chapters 4 and 5. Another thing that I think can be useful, as you might know, so here's the current $20 bill. The current $20 bill is going to be replaced by a Harriet Tubman $20 bill. Now, I don't know if you have a favorite out of these. The reason I'm bringing it up is I want to give you $20. Now, it might not be a $20 bill, might be a gift card of some kind, but I have money that I want to share with you. When I say I have money that I want to share with you, I have former students from Chemistry 1210, and they're conducting peer interviews as part of a research project that I'm up to. I think they can help you, and I think we can learn from you. So my plan is, if you complete the interview with one of these peers, I'm going to give you $20. Now, I'd like to have this take place sooner rather than later, because if it starts to extend closer to the next exam, I don't think that's going to be productive. But give me your feedback. Do you want to participate? Let me send you a poll on this. Do you want to participate in an interview? And if you complete it, you'll be getting $20. I'll also be sending everybody out an email. So if for whatever reason you can't respond to this poll, or who knows what, I'll be sending an email in Carmen that is this same idea right here. Now, when I look within here, so I'll just share the poll with folks, very high proportion, which is great. very high proportion of folks think that this would be something you'd want to participate in. I think it's going to be very useful. Now, my plan within here is I'm going to look through the data of who says, yeah, you think you might be interested, share that with my team and have them seek to contact you. When it comes to this, I'm going to be prioritizing students that I would say are more likely to be struggling in the course right now than hitting a home run. Meaning, I think I have more to learn from the student that might be an average student than if you got 100% on the first test. Okay, so if it seems like you're a little bit hanging out and you're not being contacted right away, in a sense, the higher you scored on the last exam, the least likely I'm going to contact you as ASAP. But look for that soon, and I think it's going to be really beneficial. We'll give you $20. We build to OSU chemistry department, which I always like, and I think it's going to be beneficial. Now, let's now pick up some ideas here within chapter 5. So first of all, we were looking before at ideas involving enthalpy and enthalpies of reactions. So let's bring together a few of those ideas. So at the top here, I show a chemical reaction, and on the right-hand side of it, after that, you see a change in enthalpy. This tells us the heat that's involved in the reaction. So when I look at this, I'm seeing a negative sign that's making me think that it's an exothermic reaction. And what's taking place is, if we look at sort of this depiction right here, this is from the textbook, we're going from a higher potential energy to a lower potential energy for an exothermic reaction. The products end up having a lower potential energy than which we started. We still have to use some energy to get over this bump. We still need to provide some energy to break the bonds in the reactants, but notice when they're coming together, they're moving to a lower potential energy. That's how I'm interpreting what it means to have an exothermic chemical reaction. Now take a second right here. See if you can use that information to determine, well, what would be the change in enthalpy? What's the delta H for this reaction here shown in red? Take a second, see if you can think about how we manipulated those equations. And see if you can make sense of that. In a way, I think this is related to Hess's law, because remember, within Hess's law, we manipulated different enthalpy equations. We adjusted the coefficients, we reversed them, we did different things like that. That's what I'm trying to make you think about here. Within this one, compared to the provided one, I've reversed the equation and I've cut all the coefficients in half. So I would then change the delta H, the sign of it, and if I cut all the coefficients in half, then the delta H gets cut in half too. That's what I'm trying to refresh our memory on within that. Another skill we had, something like this. So here we've got a equation given and there's a delta H value. This one says calculate the quantity of heat released when you have 5 grams of hydrogen peroxide decomposes at constant pressure. That end part, decomposes at constant pressure. Constant pressure was our constraint, or the criteria we had that meant something was an enthalpy change. So when you see that particular one, they're not asking anything tricky. They're just saying that this is going to be the enthalpy change. So take a second, think back. What would be your plan to solve this? I don't need you to race to write down the numbers. I'm going to share my plan in just a second. What would be your plan? See if you can recall the information. Would you be able to use this equation, this information, to determine the quantity of heat if 5 grams was decomposing? I think the key thing within here, recognize that when we have this delta H value, that's when we had 2 moles of hydrogen peroxide decomposed to give me 2 moles of water and 1 mole of O2. I'm using the coefficients as mole amounts, and this is the delta H that goes with it. So my approach would be something like this. I would look to see, well, what's the molar mass for the hydrogen peroxide? So 34 grams per mole, that's by using the periodic table. Then I would look and I'd say, okay, 68 grams of hydrogen peroxide results in 196 kilojoules. If I have 5 grams, how much would be involved? This would be a proportion that I would set up to determine the amount of heat that was released when I had 5 grams decomposing. Now, within that setup, could you do this with dimensional analysis? Sure, you could. I just instead set it up as a proportion. Now I know within here, what would be the main mistake a student would make? Pretty sure it would be having difficulty with the coefficients. The reason I'm using 68 grams is because when 2 moles of hydrogen peroxide is involved, it gives me 196 kilojoules. So I saw that the molar mass was 34 grams per mole, and I'm not looking at this based on 1 mole because it has a coefficient of 2. That's why I'm using that 68 grams involved with 196 kilojoules. So this is now connecting the stoichiometry of the reaction with the heat that's involved. That's something that I think you've probably been practicing a little bit. So this would be an example here of an exothermic chemical reaction. The reactants have a higher enthalpy than the products. And again, this is hydrogen gas and oxygen gas combining, kaboom, it's an exothermic reaction. Now, when I say kaboom, let me show you a video footage of this. So here's video footage of this explosion. So they show it to you that way. And when it says slow motion, then they go real slow motion. I think this is so cool. Watch this one. When I do this as a demonstration, it's over just in an instant, just in a blink of an eye. And to see it then within the super slow-mo, I think is really cool. Every time I see it, it also makes me think, well, I'm crazy standing right next to it when it explodes like that. But this idea right here, so this was a chemical reaction. So one thing we could consider are chemical reactions. In a chemical reaction, do the reactants have a higher enthalpy or do the products? Now, within this one, key idea here, in a chemical reaction, I think I need more information. Some chemical reactions are exothermic, like this explosion. If that takes place and it's exothermic and it releases heat, then I know that I have this image taking place, that they started out at a higher enthalpy than the products. But some reactions are endothermic. So my point is that for a chemical reaction, I need more data. I need some other kind of observation. I need something else to tell me if the products or the reactants have a higher enthalpy value. The reason I'm bringing that up is there's this question here at the end of the chapter. This one says, without referring to any tables, see if you can determine which of these would have a higher enthalpy value. So this is saying we're not looking anything up. We're just trying to make sense of what enthalpy is telling us and see if we can figure out which of these has the higher enthalpy value. So let me talk you through what they're about within this one. So this first example, they're comparing CO2 solid and CO2 gas at the same temperature, 1 mole of each. I think it takes energy to go from the solid to the gas. I have to add energy to go from the solid to the gas. I'm adding energy. The gas is at a higher enthalpy. So for a phase change, I don't need any additional information. I know that a solid has a lower enthalpy than a liquid. And I know a liquid has a lower enthalpy than a gas because I have to add heat to go from one to the next to the next. So in this case, I don't need any additional data to answer it. Part B, I don't need additional data either because it says compare 2 moles of hydrogen atoms versus 1 mole of H2 molecules. What they're trying to get at here is the bond formation is always exothermic. If I have 2 hydrogen atoms separate from each other, as they come together to form a bond, it's an exothermic process. It's moving to a lower enthalpy value. So that's what they're trying to get at within this one. They're trying to get at that bond formation is always exothermic. Take a second within this one. Read that description for D. I'm going to send you a polling question on this one. Well, I'll tell you what, I'm not going to send you a polling question on that. My bad. I'm going to send you a polling question in just a second. I want to explain this one instead. So within this one, if I were to rank these two, I've got the same amount, 1 mole in each case. It's N2 gas in each case, but they're different temperatures. I know that in order to raise the temperature, I have to add heat to it. So this would be another one that I don't need any additional data to know that the N2 gas is at a lower enthalpy than the N2 gas when it's raised to 300 degrees C. The only one I need data for is choice C, question C. And the reason the book gives you a chemical reaction and asks you to somehow come up with the answer is because they include this image within the chapter. They include the fact that this is an exothermic reaction. Now, when I look at these different ones, what I found myself thinking is, well, what would be another example? Anytime I got to end a chapter question, I always think, well, how else could this be asked? What else might they be looking for? So what occurred to me within this one, another related one would be a comparison like this. Which of these would have a higher enthalpy value? Is it 1 mole of N2 gas at 100 degrees C, or is it 2 moles of N2 gas at 100 degrees C? Let me send you this one as a polling question. So without looking anything up, which of these do you think has a higher enthalpy value? Take about 10 more seconds. So we got a pretty strong consensus that it's larger for the 2 moles versus 1 mole. I'm going to agree, okay? 2 versus 1, well, 2 is bigger than 1. How does that fit into this different part right here? It comes back to this other feature of enthalpy. Enthalpy is an extensive property. If you double the amount that's there, you double the enthalpy value. So this is one more feature that I would say I don't need additional data. I know that if I'm comparing apples to apples, same substance, same temperature, if I have more of it, the enthalpy value is higher. So right here, very typical exam question that I have right here. Question 5.42, end of chapter. Being able to qualitatively understand enthalpy values, really common exam question. A topic that we had from the pre-class video and I thought people were doing a great job with is looking at what are called enthalpies of formation. 2 different tasks within that. We want to be able to identify a standard enthalpy of formation reaction. That's what that symbol is right there. That lowercase f is designating something involving the formation, and we want to be able to use those. So here's a question that I posed within the video. And this was asking, well, which of these is a standard enthalpy of formation reaction? The answer was A. The different features that we had within that, I thought people had really good questions and considerations of it. So here's a very common question. Well, what did it mean to have these fractions involved? A lot of people were asking about that. What is that breaking some kind of rule? Why do we have fractions? Why is it okay to use fractions as coefficients now? In this student's response, they were getting at part of the point here. Said, well, maybe it has something to do with the fact that they are describing very specific combinations between the elements, that it's describing something very specific. I agree. What we're doing within here is we're recognizing that the coefficients that we have in a balanced equation, they're telling us the proportions for how the reactants combine to produce the products. Back in chapter 3 and 4, it was really useful to have those be whole numbers. It made it simpler to see the proportions, to see the relationships. Now, when we're going to make comparisons, we want to make it so that we're always thinking about what does it mean to make 1 mole of product. So that's what we're going to have for any of our standard enthalpy of formation reactions. They're always making 1 mole of a particular product. You know, the balanced equation, we're not breaking any rules. It's just a tool that shows us the different proportions. And in this case, when we're looking at the standard enthalpy of formation, it's going to be for 1 mole of product. So when I have these, if I'm trying to evaluate them, the variables I'm looking at, well, first of all, I have to have 1 mole of a single compound being found as a product. In choice C here, well, I got a lot of different things as products. I need to have only 1 mole of a single substance being formed. When it comes to the reactants, I need to have them so that it balances. Fractions are okay for coefficients, no big deal there. And the elements have to be in what are called their standard state. A lot of questions that I saw within this. So first of all, elements in the standard state, that means how are they found on the periodic table with everyday conditions of temperature and pressure? That's what it means for standard state. So I list here different examples of ones that correspond to being in the standard state. A lot of student questions was, well, are we supposed to memorize these? What are we supposed to know? How do we make sense of it? This is what I think that you should memorize or understand. And I think many of this you already do. I want you to know the diatomic gases. That's a skill that I think you already have. Those are the elements in their standard state when we're looking for things like oxygen, hydrogen, chlorine. You know the diatomic gases, so we want to be able to recognize that those particular elements are found as diatomic gases in their standard state. Next, we have many metals on the periodic table. Those are solids. Metals are solids. Whether I'm looking at iron or sodium or calcium or lithium or magnesium or chromium, I could go on. All of those that we have on the left-hand side of the periodic table as metals, those are all solids. The only exception I have is mercury. And I think if you've seen a mercury thermometer, you've seen mercury as a liquid before. Okay, that's the only metal that you're going to have to know exists as a liquid. I finished with 2 ones that are novel. These are cool. Add these to your memory banks too. When we're looking at the elemental form of carbon, it's when the atoms are arranged and it's forming what's called graphite. Carbon, when the carbon atoms are arranged to form diamond, that is a different structure for how the atoms can be arranged. We're going to look at that in chapter 12. I mean, it's really remarkable. Graphite and diamond are both 100% carbon, but they really have different properties, right? So we're going to look at that more in chapter 12. One other one to bring to your attention, which I think is also cool, is the elemental form for sulfur. It's in this 8-membered ring. So just like we have diatomic molecules, chlorine, hydrogen, oxygen, those come in molecules where the 2 atoms are paired together. It turns out for sulfur, the elemental form is this 8-ring molecule. So as far as what to remember, let's remember our diatomic molecules, our metals are solids. Mercury is one exception to that. Graphite is the standard state for carbon, and sulfur is this 8-membered ring. This, I think, gets us all the standard states that we need to know. So we practice this a couple different ways. And I was pointing out here that these questions can be asked a couple different ways as well. So this one says, if the heat of formation has this particular value, which of these would be the thermochemical equation for it? It's really just asking which of these is correctly listing the standard enthalpy of formation for the reaction leading to H2O liquid. So when we're evaluating this one, I like this student's comment. I originally answered to E without thinking as much and got it wrong, but went back and realized that my error was having a coefficient of 2 rather than a coefficient of 1. Several people were sort of thinking about this. I mean, we're used to having whole numbers, but now we're changing the game a little bit. So I agree that after going back, I think D is the best choice here. Here's another one that was within the video. And I brought this one up because I wanted to say, let you know, once again, that symbolism right here, delta H raised to the 0 superscript F minus, this is saying the standard enthalpy of formation reaction. So as we're looking at our choices for here, I thought this comment was, this response was interesting. So this one said they thought D was going to be correct. They ruled out A, B, and C because when they looked at the products, those were all leading to 2 moles instead of 1. So they ruled out A, B, and C. I think that's a good move, ruling out A, B, and C. They point out that option D is balanced. However, they weren't that sure because they started to think about, well, the H2O, is that what it should be as a liquid if it's in its elemental form? They weren't quite sure. So let me give you one more format that I've seen on exams. Another question format would be something like this. It would ask you on the test to write the standard enthalpy of formation for H2O2 liquid. And then it would ask something like, well, what are the reactants? It's not asking you to select the correct equation. It's asking you to write it and then interpret it. So think about that for a second. If this was a question, write the standard enthalpy of formation reaction for H2O2 liquid. Look at your equation, think about it. What are the reactants that you have? I think the elements in their standard state, if you need to have hydrogen in the compound, you need H2 gas. If you need oxygen in it, you need O2 gas, because those are the elemental forms when you need to get hydrogen and oxygen. So that leads me to think within here, D wouldn't be correct, because I don't want to have water and O2. I needed to have H2 and O2 leading to that. Now, I've shown a few different ways that these questions can be posed. To solve them, it's the same process in all of them. We have 1 mole of a single compound being found as the product. Fractional coefficients are quite possible for the reactants, and we're going to be looking at the elements in their standard state. Now, this was one of the tasks, being able to identify the standard enthalpy of formation reaction. Let's see, what does it mean to now use them? So I stepped through within the video something that I'm going to go pretty quickly through here. The idea is that you could use standard enthalpy of formation values, and you could apply Hess as well. You could manipulate them. You could see, what does it mean to reverse them, to combine them, to get and use them for a target reaction. That's what this top portion is showing, and then that's what's being depicted here in the figure. It leads us to this idea right here. We can break down any reaction into the corresponding formation reactions. And we can use that data then to come up with the delta H for the overall reaction. It's being used by looking with the standard enthalpy of formation values that we have and simply combining them. The idea is that you can start with particular reactants, and then conceptually you can say, what does it mean to break them apart into the parts, into the atoms themselves, and then bring those together and consider, where do you end up for the products? This does not have to take place in real life. This reaction right here, I don't think we break it apart into carbon graphite and O2 molecules and H2 molecules and then bring them back together, but we don't need to. Enthalpy is a state function. We can just conceptualize that taking place and then do the math accompanying that. So in order to do the math, well, we need provided data. So for a standard enthalpy of formation question, you will get provided data. Here's a table from the book. You do not need to memorize this information. The data that you need for a standard enthalpy of formation question, it'll be provided within the question. It'll be provided within a table. It will be given to you on the test. Now, recognize that within here, if an element's in its standard state, its delta H value is 0. And the reason why is, if I were to say, well, what is the standard enthalpy of formation for H2 gas? I would put 1 mole of H2 gas, and the reactants would be coming from the element in their standard state. Well, it's the same thing. There is no enthalpy change. So that's why for any of the ones that are the elements, if they're already in their standard state, they don't have a value because their value is 0. So here was the example that I worked through. So in the example, I said, if we use provided data, we could determine the enthalpy change for the combustion of methane. Here's a balanced equation for that. The provided information includes delta H values for the methane, which is a reactant, the CO2, which is a product, the H2O liquid, which is the product. There's no value listed for O2. It's not because we're being cheap and we can't afford it to give it to you. It's because it's a value of 0. So when we compile the data, we're going to look at the standard enthalpy of formation values for all of the products minus all of the reactants. So here I show the math for all of the products. I've got 1 mole of CO2 and its value, 2 moles of H2O and its value. Products minus the reactants gets me the overall delta H value. Now, when I've studied this one, as far as what errors do students make, 2 different things. The 2 most common mistakes are they don't account for the coefficients. Notice within here in the balanced chemical equation, it included 2 moles of H2O. In my table, it's listed as kilojoules per mole. That's why I have to make sure that I use that value twice, the 2 moles of H2O. So failing to account for the coefficients, very common mistake. Even more common, messing up the sign along the way. Because we have this combination of some of the values are negative, well, in this case, they're all negative. We're doing negative minus a negative. It can be a mess right here. So in my own approach to keep it clear, I put brackets around it. I put brackets around all of the products minus, and then brackets around all of the values that I have for the reactants. That helps me keep track of the sign a little bit. So you just have to be a good accountant when you're doing that. This is using then provided standard enthalpy of formation data. So here, as far as suggested problems, the ones at the top, both of these are skills that I just mentioned. The one at the top would be to write the standard enthalpy of formation reaction. And I think we could do that for any of them. And at the bottom, it would be using these, and these would be setting up that math of products minus reactants. It says to look to Appendix C. On your exam, that data would be provided within the question itself. Now, this last idea that we have in the chapter, this is a new one. Okay, this is using bond enthalpy data. This is another way that we can calculate the enthalpy change for a reaction. It's another type of provided data. So here's the idea. So first of all, look at this case right here. Let's say we are doing a reaction. These are the reactants. It's CH4 and CO2. Here's the product. And we had to go in between to get there. So take a second. Based on that image right there, do you think this is describing something that's endothermic or exothermic? This particular reaction as written, what are your thoughts? Endothermic or exothermic? Take about 10 more seconds. So to share the results right here, we're really close to having 75%, 25%. Really close for our distribution right here. Now, within our with most folks saying it's going to be exothermic. Now, within this one, when I wrote the question right here, I tried to include endothermic or exothermic, but then I won't say to fool you, I tried to give a rationale for this because you know how it shows up on the test. There's usually ones where, well, that sort of seems like it might be right. So this idea here for endothermic, because there's initially a large increase as you're breaking the bonds, I agree that that is taking place. But if we're looking at the overall process as endothermic or exothermic, we're comparing where we start and where we finish. That is what's corresponding to the delta H of the reaction. So I would say in this case, this is describing an exothermic reaction. And it's because the enthalpy of the products is lower than that of the reactants. This would give off heat. If we were to look at the internals on that, it took energy, I think, to break the bonds. It always takes energy to break a bond. But then we had the exothermic bond forming, and that was releasing energy. And if I were to compare these two, I end up at a lower enthalpy value than I started. That makes the entire process exothermic. This idea of talking about the energy pertaining to the bonds That's what is in this last category of bond enthalpy. So as I think about it conceptually, bonded atoms are always at a lower potential energy than if the atoms were broken apart. It's a misconception to say energy is somehow stored in the bonds. The bonds are, when they're bonded, they are at a lower potential energy than if they were separate from each other. It always takes energy to break a bond. And energy is always produced as the bond is formed. This image right here, this is called a potential energy well. This is really similar to how we started chapter 5. We've got the atoms far apart from each other. As they come together and a bond forms, they move to a lower potential energy. Here's a table showing the data for different bond enthalpies, the energy corresponding to different bonds. We have examples of bonds between carbon and carbon, carbon and hydrogen. Now, the way that we interpret this, bond enthalpy is telling me it always takes energy to break a bond. This is how much energy it takes to break a particular bond. A typical carbon-carbon bond takes 348 kilojoules per mole. A typical nitrogen-hydrogen, 391. This is, again, provided data for you. This is saying how much energy does it take to get out of this well? They're stuck together. How much energy does it take to separate them? If I want to think, well, how much energy do I get when the bond is formed? It's still the same magnitude, but that's going to be an exothermic process. That's telling me the same information about the depth of the well, but it's going in the other direction. It's saying they started out apart from each other. Now the bond is forming. So my point is that these provided data right here, they can be viewed as being endothermic or exothermic, depending if we're going to use them to think about breaking the bond or forming the bond. So within the book, it describes it this way. It says, when we're using this bond enthalpy data, we can imagine as if this process takes place in 2 steps. We're going to add energy, first of all, to break the bonds. That's what takes it to a higher enthalpy. And then we can conceive what happens when we form the bonds. When we form the new ones, that's the exothermic process. When it says we can imagine that taking place, enthalpy is a state function. As long as we have the math, we can do it. That doesn't have to be what literally takes place. So the book has this expression right here, that when we're looking at the delta H for a reaction with these bond enthalpies, we can do the energy of the bonds broken minus the bonds formed. What this is really doing, it's saying that it is endothermic. It's a positive value to break bonds. And it's exothermic. It is a negative value when the bonds are formed. So this equation right here, I know it's within the book. I'll be honest with you, this is never in my head. I never think about this. I want to have a deeper understanding that it's endothermic to break a bond, and it's exothermic with a negative sign to form a bond. That's what's in my head when I'm solving these. So within this example right here, here's provided average bond enthalpy values. It points out in this example, what would it mean to break the bonds in the reactants and form the bonds in the products to get the overall delta H? And it sees that you need to break 1 mole's worth, because the coefficients are going to be in mole amounts. You need to break bonds of carbon and hydrogen, break bonds of chlorine and chlorine. Those would be endothermic. And then you're forming bonds in the product. So you're looking now structurally, what bonds do I need to break? Which ones do I need to form? And that's what the corresponding math corresponds to. There's an endothermic process when we are breaking the bonds. Always takes energy to break a bond. And an exothermic process when we get that energy back during the bond formation. That's what's taking place in the process. Now, when I see this question on exams, it almost always has a setup like this. So let me talk you through the arrangement here. So notice within this one, I see provided bond enthalpy data. There's a balanced equation at the top, and then there's this image right here. This image is showing you the bonds that you are going to have to break and form during that reaction. About a month from now, you're going to learn a lot more chemistry, and you're going to be able to draw these structures yourself. But at this point, We're not quite there yet. So you can quickly recognize on your exam when it shows a image like this, it's trying to show you the bonds that are involved. Now, if you look more closely at it, notice it's still including the coefficients. You have 2 moles of this molecule, 7 moles of the O2, 4 moles of the CO2, and 6 moles of water. But the added information now is it's showing you the actual bonds that are involved. 1 line is what we call a single bond, 2 lines is a double bond. They have different values in the table down here. So this is the way that I'd answer this one. If I want to get the overall delta H, I'm going to start and say, okay, endothermically, I need to break bonds. And when I do this one, I put a little X over it as I'm working it, just to make sure that I'm counting the bonds correctly. When you have a question like this on a test, I really recommend that you see about make a sketch, do what you can do, and cross out as you work through. Because this is what I then find. I see that, first of all, I'm going to break the carbon-hydrogen bonds. That has a value of 413. And I see within this molecule, 1, 2, 3, 4, 5, 6. I get to a value of 12, though, because I have 2 moles of that. I had 6 bonds within that, and then I have 2 moles of it involved. That's where I get this 12 moles value. I'm going to break this bond within this between the carbons. I look up a carbon-carbon bond, and I see that I have 2 moles of that, again, accounting for the coefficient. If you follow with me, how about within the O2? Within the O2, I got a value of 495 and a coefficient of 7. This would be all of the energy that it takes to break apart all of the bonds. All of the bond breaking has this very endothermic value. Now I'm going to say, what does it mean now to form the bonds? And within my bookkeeping, what would I have? I have a total of 8 moles of carbon-oxygen double bonds, 2 within the molecule, and then the coefficient of 4, and a total of 12 of the oxygen-hydrogen bonds. 2 within the molecule, coefficient of 6 gets me to 12. So then I'm going to combine the 2 parts. Bond breaking was endothermic minus then a value that's exothermic for the forming. That's how I get the overall delta H for the reaction. So this is a final skill that we want to have in chapter 5. The kinds of questions that I just discussed within that second portion, here's one where they're saying, without doing any calculations, qualitatively predict the sign of delta H. I'm really confident you'll have a question related to this on your exam. I'm also really confident you're going to have a question similar to this one. Within this one, notice, as soon as I see the images, I know I'm using bond enthalpy data. And that's what it's directing me to in table 5.4. Okay, take a second within here. I'm curious within the chat. I've discussed a lot of ideas within chapter 5, but we've had it spread out a couple of days. Right now, give me your own self-assessment. What is your relative confidence with ideas in chapter 5? You can go from you feel really confident to you just, chapter 5, I don't even remember chapter 5. Tell me in the chat, what is your general assessment of your understanding for chapter 5? I saw one question as those are coming in. Back to the bond enthalpy question, it was how do you determine if something is a single bond or a double bond? Right now within that, that is going to be shown with either a single line, or 2 lines. A single bond is being shown with just a straight line. A double bond, you see 2 of them that are parallel. And that's what you then look to match up within the table. Couple questions that I'm seeing here or comments within chapter 5, as far as where you're at within your current understanding. The stuff that we were working on within the first half of class tonight, whether it was the bond enthalpy values, whether it was identifying standard enthalpy of formation, or using standard enthalpy of formation, for all of those parts, I think mastering does a really good job with that. Mastering does a really good job because those are things that you can easily set up within the format for that. So when I'm seeing folks as far as having, what does it mean to try to practice more of these? Move ahead to what is already available right now in Mastering, okay? Move ahead within that, because I think that it's going to do a really good job in the next couple assignments, the ones that are due Friday, and even the one that's going to be due at the start of next week. I think chapter 5, that's a strength for Mastering, meaning I think it's really well aligned with what you're going to have to do on the test. Okay. And I think that the video that I'm preparing, I think will also give you some good insights as far as ideas from both chapters 4 and 5, things to practice, things to work on. Now, I'm going to move on now within the second half of class and begin to think about some ideas within chapter 6. We've got the second half of class here, and then we've got both classes next week. That's what we have leading up to our test. We've got a lot of ideas here within chapter 6. I want to be very specifically focused on the ideas and what you're going to need to do with those. Because the sooner we can begin to get through these and then give it a little bit of time to think about it, I think the better we're going to be prepared to head into the test. So what I want to do tonight, I want to get it started. 2 of the things that we had within a pre-class video looked a little bit at properties of light and this idea of quantized energy. And then I'm going to spend some time looking at a new topic as time allows, which is Bohr's model of the hydrogen atom. Do your best to hang with me within here, because I think it's going to be time well spent for us. So within this one, this is a summary slide that's from the pre-class video that brings together the features that we want to know when we're thinking about the electromagnetic spectrum. This is sort of a summary slide for that whole first section. So what do I find within this one? First of all, we want to be familiar with wave descriptions for light. And when I say light, I'm talking about different regions of the electromagnetic spectrum. Maybe it's visible light, maybe it's microwaves, maybe it's blue light, maybe it's X-rays. For all of those, when I think about those as having a wave description, one feature I'm interested in knowing is the wavelength. That's what's given that symbol lambda. The wavelength is defined as starting from one position and seeing when that repeats again. So you can start from the top of a peak, from the crest, and then the crest to crest distance, that would be what the wavelength is. Next feature that I want to bring up, there's a relationship between the wavelength and the frequency. Lambda corresponds to the wavelength. The symbol nu corresponds to the frequency. If you multiply the wavelength and the frequency, that equals the speed. Many of the times when we're working on our problems in here, the speed for light is going to be a constant. That's what c is. It's a constant. It's called the speed of light, 3 × 10⁸ meters per second. That's a constant that would be given to you on test, but I think within chapter 6, you're going to quickly memorize it, okay? 3 × 10⁸ meters per second, that's the speed of light. I also find it useful to know the conversions when we're going between meters and nanometers. That's a new metric value for us, right? We've been talking a little bit about centi, milli, kilo. In this chapter, we're going to add nano. 10 to the 9th nanometers is 1 meter. This is another metric conversion that we want to add. At the bottom here, I show a very typical calculation involving C equals lambda nu. It says calculate the frequency of red light that has a wavelength of 725 nanometers. It's using this expression right here where the speed is a constant. We're solving for the frequency and the wavelength is given. So we've got 2 out of 3, we're solving for the last one. What I'm trying to illustrate within this last one right here, red light has a wavelength of 725 nanometers. The visible light region, it's in nanometers. So that's why I find it useful to have memorized what is the speed of light in nanometers per second. It saves me a little bit on the conversion. So instead of 3 × 10⁸ meters per second, it's 3 × 10⁻17 nanometers per second. I find that to be a useful conversion. You know, if you can write stuff down and have it available on a test, I would write that down, okay? Write down the speed of light both in meters per second and nanometers per second. I think you'll find it useful. When we have the different regions of the electromagnetic spectrum, you do not need to memorize specific values within this, but you do need to know how to place them in order as we go from gamma rays all the way down to the radio frequency. You need to place them in order in terms of these different terms. When I'm looking at the left-hand side right here, this corresponds to a high frequency, a short wavelength, and a high energy. Gamma rays are way over the edge of being the highest frequency, the shortest wavelength, and the highest energy. Then come X-rays, then the ultraviolet. Then I've got going from violet light all the way to red light, infrared, microwave, and then I reach down to the radio frequency. At that extreme right there, those are the lowest frequency. They're the longest wavelength, and they're the lowest energy, smallest energy. So we want to be able to order them with those different terms. So here's a couple questions that I saw in the chapter pertaining to this. So first one right here, it says, consider the two waves right here. Let's think about these as being electromagnetic radiation. So first of all, part A says, well, compare the wavelengths. What would be the wavelength? I think I could actually calculate the wavelength value because look, it shows me what does it mean to go starting here with 1 cycle, 2 cycles. I know the distance for that. The wavelength for part B would be half of that particular value. So I think I could actually calculate what the wavelength is given that information. I could convert it to the frequency too, because I could use the speed of light. On a test, you're going to have the speed of light will be given. 3 times 10 to the 8 meters per second. Or we could have the value in nanometers like I just mentioned. This third part right here, it says identify the region of the electromagnetic spectrum. That last part, I wouldn't expect that on the exam. You do not need to memorize specific wavelengths, specific frequency values, but you do need to be able to put them in order. So when I say you do need to be able to put them in order, I've seen this format used quite often on tests. So this one says, which of these statements are true? Take a second, read this one through for me. Notice within here, in order to answer this, you have to know the ordering of the electromagnetic spectrum, and you need to be able to think about it in terms of things like energy, frequency, wavelength. I think you have 2 true statements within this one. I think gamma rays are higher in energy than X-rays. They're further to the left. X-rays have higher frequency than blue light, so it's now doing a comparison between those two. I think that part is true. We have a comparison involving UV and microwave for wavelength and infrared being more energetic than microwaves. So I know right here as I'm throwing this at you, first thing that you need to do is you need to get a sense of what is this ordering? Then you need to get a sense of how does it connect to these different terms like energy, frequency, and wavelength. I know right now, if you're seeing this for the first time or first time in a while, it's a lot of information. So I think though that this is a very typical question, okay? It's a very typical thing that you're gonna be asked to do. A qualitative one of putting them in order, again, in terms of things like wavelength, frequency, and energy. The thing that I'd be careful with, be especially careful when you're thinking about wavelength. A long wavelength means it's lower in energy. That's by far the most common mistake. High frequency is high energy. And because wavelength and frequency are inversely related, a long wavelength means it's lower in energy. That's the main thing that students make a mistake on. Next section, 6.2, that's where it begins to introduce the idea of quantized energy. So I see 2 different objectives here. One is talking about black body radiation and the photoelectric effect. And the second one now starts to look more closely at what are called photons. So within this one, when we're talking about the black body radiation, within the pre-class video, I explored a little bit, what did that profile look like? How did the profile change when the temperature of the object changed? And I pointed out that the classical description, and by classical, I mean the physics ever since Isaac Newton all the way up to about 1900, it had worked for centuries. It did not work in order to explain black body radiation. It suggested that the profile should just go up, 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 up. But experimentally, that wasn't the case. This is a really groundbreaking event. In a way, this broke classical physics. The physics that had worked for centuries began to break down because it couldn't explain features like this. The person that we associate with sort of this new era right here is Max Planck. Within his analysis, his explanation for this black body radiation profile, he made something that he included within it that at first he thought, well, this can't be right, but it turns out it is right. It's summarized in this expression right here, E equals H nu. This is saying that if we look at the frequency of the light and the corresponding energy, it has Planck's constant, which serves as a scaling factor here. What this is saying is, for a given frequency of light, let's say we're looking at red light, it has a particular frequency. This is saying that there is a smallest amount of red light that you can have, in terms of its energy. You can't just keep dividing it up smaller and smaller and smaller. You're going to have a smallest amount of red light. It's going to have a specific value to it. It's going to be quantized. It's going to have a specific value to it. If you think about this, a lot of times you sort of have this analogy of having a staircase. With a staircase, it is quantized, meaning you can be on one step or the next step or the next step. There are specific potential energy values that you can have. But what makes this even stranger within this idea of things being quantized, this is saying that you can be on one step or the next step or the next step, but you're never found in between. If you're truly quantized, it has one value or another value, but never somewhere in between. People are making some nice connections between this and Millikan's oil drop experiment. That's what Millikan was trying to figure out. He wanted to figure out, was the charge on the electron quantized? Did it have a specific value, or could you keep dividing up the charge smaller and smaller? And as you know, what he found was there is a value that the electron has. There is a specific value. You can't take an electron and cut its charge in half and cut that in half. There was a minimum value that it has. In a way, that's what Planck is saying. He is saying that energy, when it interacts with matter, must have the smallest threshold value. Another one that's expressed within here is on Einstein's interpretation of the photoelectric effect. Einstein was aware of Planck's experiment or his explanation for black body radiation, and he used it when he was trying to explain this phenomena. And by this phenomena, this is one that was I presented in the pre-class video, the idea that you could shine light onto a metal surface. Electrons could be ejected from that surface, but only if they had high enough energy. Only if their frequency was high enough. Einstein went to the equation E equals H nu, and he used that to determine the energy of the light that was striking the metal surface and causing an electron to be ejected. This was the energy for what he called a photon. Just like if you're a Star Trek person, they talk about photon torpedoes, same word, photon. A photon is like a particle of light. The smallest amount of light possible, a particle of light. Now within this experiment, a couple of takeaways for us right here. The frequency of the light is crucial. It must be above this minimum threshold value. If it's below that value, no electrons are ejected. It must exceed, if you see within the book where it calls it the work function, that is the minimum amount of energy needed to remove an electron from that metal surface. In this experiment right here, that light, it acts like a particle, which we call a photon. Each of these photons has an energy E equals h nu. Now, why is this novel? Why is this unusual? Why is this unexpected? Because in other experiments, light acts like a wave too. Light can be diffracted, it responds when it goes through a prism in a certain way, it can be refracted. A lot of experiments show that light is a wave. This is an experiment that is suggesting that light is behaving like a particle. So we've got two strange ideas that I'm introducing here at the start of chapter 6. One is the idea that the energy is quantized, that energy can't be just divided up smaller and smaller. It has a particular value, a smallest value it can have. The second thing I'm introducing is that light appears to have characteristics both as a wave and in other experiments of a particle. Both of those are strange ideas. Both of those are revolutionary ideas. Both of those, if you said, hey, I think I've got some insights, and you were around in 1900, they would have locked you up, okay? They were both very radical ideas, but we're going to see in chapter 6, they're both radical ideas that are actually how our world works. Now, I noticed within here a couple comments. So I've seen that a lot of people were trying to make connections between this and other things that we've seen. This discussion here about connecting it to the activity series, I think that those are good insights. They looked at the different experiments in here as far as what did it mean to cause electrons to be ejected or not. And this idea of how does it work and connecting it to the activity series, I thought those were good connections. We're going to learn a lot more about this in chapter 6 and then in chapter 7, but I like this idea of connecting it back to chapter 4, because what takes place after all? All of these are oxidations. All of these are saying, what does it mean to remove the electron from the metal? And so sure enough, it does make sense that something that it would be more difficult to remove an electron from, like platinum, it takes a higher frequency in order to cause that to be ejected in the photoelectric effect. Those are really good comments people were making. Now, let me step through some calculations within here to then sort of show you how this idea shows up with different things that you're asked to do within the chapter. So this one right here is describing the experiment. Titanium metal requires a photon with a minimum energy of a certain number of joules to emit electrons. It's saying that when the metal surface is titanium and you're shining light on it and you're going to cause electrons to be ejected, that light must have at least 6.9 times 10 to the minus 19 joules to emit the electrons. So notice then the different things that they ask you to consider within here. So the first one is, what would be the minimum frequency necessary? What this is asking you to do is use the equation E equals h nu. You're given the energy in joules, use Planck's constant, and now solve for the frequency. Now, I saw a couple people within here asking Planck's constant. Is that something that you need to memorize, or should you know it? I'll answer it this way. Planck's constant is going to be provided on your exam. Planck's constant is going to be a constant that's listed for you to use. But I'm also going to answer it this way. If you have seen the show Stranger Things, you should memorize Planck's constant. Tell me in the chat, do you know what I'm talking about? If you've seen Stranger Things, do you understand why I say you should memorize Planck's constant? I don't think it's much of a spoiler to say that, I think it was in the very last episode last season, came down and there was this crucial scene and the password was Planck's constant. You needed to know Planck's constant. And so I'm watching this with my wife. She's not a scientist. And she looks at me and she's like, Planck's constant, huh? Do you know Planck's constant? And I could proudly say, yes, I know Planck's constant. So, you know, for what it's worth, I sort of got some cred watching Stranger Things when that came up. Okay. Next thought within here, back to the question. We've calculated what the frequency is. Second would be, well, what would be the wavelength? Now we're using that second equation. Within this question right here, both of these equations are relevant. E equals h nu and c equals lambda nu, we want to be able to go back and forth and use both of those expressions. We used one of them to calculate the frequency. We're using the second one to now calculate the wavelength. In that section, we want to go back and forth, be able to use both of these expressions. Next question is, would it be possible to eject electrons if you use visible light? For this one, I would look at this provided data right here. I've just calculated that it will work with 286 nanometers. Would it work with 400? It won't. 286 nanometers, that is higher energy than the 400 nanometers. So I'm using this one right here to say, no, if you're at 400 nanometers, you don't have sufficient energy. I don't care how bright the light is, how intense it is. If it doesn't have the correct frequency above the threshold value, it won't eject any. This very last one right here, I think is the most involved. This one's saying, okay, what happens if you use light of 233 nanometers? What's going to happen then? What happens then is that is sufficient to eject the electron, and the extra energy that you have, the energy above that threshold value, it gives it kinetic energy. It gives it a boost. So the way that I'd solve this last one would be this. So first of all, I converted 233 nanometers to the frequency, and then I use the frequency in E equals h nu. That's what I mean by going back and forth between both of those expressions. So when I'm using photons with 233 nanometers, this is the energy that those have. I also know that it took 6.9 times 10 to the minus 19th to eject them. So the difference between those, that's how much kinetic energy would be imparted. My main takeaway within this one is we want to be able to interpret the phenomena, and we need to be able to use both of these equations. Here's another way that I've seen both of these equations used in questions. So this is another 6.30, another end of chapter 1. This one says, the energy from radiation can be used to rupture chemical bonds. A minimum of 242 kilojoules per mole is required to break the bond in Cl2. This would be the bond, this would be the bond enthalpy value. Those are in kilojoules per mole. What would be the longest wavelength that you could use to break that particular bond? So this one's got an important feature that I need to point out for you. This is again using the relationships E equals h nu and C equals lambda nu. Constants that are given are things like the speed of light and Planck's constant, 6.626 times 10 to the negative 34 joule seconds. The key thing that you need to do within this one is recognize that this energy right here to break the bond in Cl2, its bond enthalpy value is in kilojoules per mole. So if we are shining the light on that, instead of asking the question, what would it mean to break a mole's worth of those bonds expressed in kilojoules? We are asking, what's the energy it's needed to just break one of the bonds? So I need to think about 242 kilojoules per mole in terms of just one of the bonds. I could use some dimensional analysis to figure that out. It takes 242 kilojoules to break 1 mole's worth. 1 mole of those Cl bonds would be 6.02 times 10 to the 23rd bonds. That's how many I have in a mole. And then I have a conversion between joules and kilojoules. Notice within here, the energy that it takes is a very small amount because I'm looking at the energy just to break one of the bonds. When I have 242 kilojoules, that's because I have a whole mole's worth of them. So I know within here, before I can use this expression E equals h nu or C equals lambda nu, I need to figure out what energy am I talking about. When I use E equals h nu, that's for 1 photon. 1 photon can break 1 bond. That's how I would then seek to solve this. So now since I know the energy that's involved, I can plug that into E equals h nu to figure out, okay, this would be the frequency needed. And if you want it in terms of wavelength, no problem. I'm going to use C equals lambda nu to convert that. If you want it in meters, I'm good to go. If you want it in nanometers, I'm going to use that conversion that I have, knowing the speed of light is 3 times 10 to the 17th nanometers per second. So I know that this one right here, a lot of information on the slide. what I'm doing within here, again, two different features. I'm using both of these equations, E equals H nu and C equals lambda nu. I'm using both of those because one is involving frequency and the other one is now saying convert the frequency to the wavelength. That's why I have both of those. And the key step within here is I first need to figure out what energy am I talking about. And I used and converted from kilojoules per mole. And instead of having a mole's worth, I wanted to know the energy in joules for just one of the bonds. This is something, I'll work another example so we can sort of practice this and see this again. I want to move a little bit now conceptually to get a head start on our last idea. Our last idea that we're going to begin tonight, looking at Bohr's model of the hydrogen atom and where this comes from. So if we think back to chapter 2, we began with a billiard ball model of the atom. We began then to add some features to it. J.J. Thomson gave us the discovery of the electron when he calculated the charge to mass ratio. We had a specific value for the charge in Millikan's oil drop experiment. And with Rutherford, we had this insight that it seemed that there was a dense positive nucleus in the center of the atom, but most of the atom was empty space. This is sort of where we left off what atoms were like in chapter 2. In chapter 6 now, we're going to move towards what our modern understanding is. And that's going to begin by looking at what Bohr's model of the hydrogen atom was. Within this section, 6.3, a couple of different topics come up. The idea of what's called the line spectra for hydrogen, Bohr's model, and then looking at the energy that's involved for the hydrogen atom. This right here is a depiction of Bohr's model. In the center, we have the proton in the nucleus, and we see these different rings around that where the electron could be found. Now, I'm curious within here. Based on your prior knowledge, whether it was in high school or somewhere else, have you heard of the Bohr model? Tell me in the chat. What is your understanding? Is this something that you heard before and you forgot, you never heard of? You've got a good understanding? Tell me your view here. Where do you stand on the Bohr model? So I'm seeing a range of responses here from yes, something you're familiar with, to yes, but I forgot it, which I get. And a few folks within that say, no, this is entirely new, which is fine. So thanks for feedback, that helped me out. Within this one, when it comes to the Bohr model, one thing that we want to take away from the book, this is not going to be our final model. As the authors point out, this is an important step along the way. So we're going to spend a little bit of time in chapter 6 looking at this model because there's a few things that we're going to take away from it. This is not our final picture. We're going to get to our final picture next week, but there's a few features that we're going to use from Bohr that we're going to find in that final model as well. And that's what they're shown here at the bottom. What we're going to keep is the idea that electrons, they're going to be found in certain discrete energy levels. And we're going to use quantum numbers to describe features of those energy levels. And we're going to see that an electron can move from one energy level to another one, and that involves energy. Those are things that we're going to use when we move on to our more complex model in next week in chapter 6. But let's spend a little time within the Bohr model itself. And where did it come from? So a phenomenon in the late 1800s was this idea right here. If you take light, white light, shine it through a prism, it gives you the entire range of colors. Roy G. Biv, it gives you the entire visible spectrum if you start out with white light. A line spectrum is one that doesn't give you all of the colors. It gives you certain specific colors. Now, how might you get a line spectrum? Something like this. If you take gas, like hydrogen gas, You put it in what's called a discharge tube here. You send electricity through that. If you take the emitted light from that and send it through a prism, now what you find is it breaks apart into specific colors. That's what's being shown here. When you use it with hydrogen gas within there, you get specific lines. It's not giving you all the colors. It's just giving you specific ones. If you use a different gas in there, like neon, it gives you different ones. If you've heard of a neon lamp, that's what they're doing. They're putting neon gas in a tube, sending electricity through it, and then these are the different wavelengths then that are emitted. So when you have a line spectrum, you get a small number of distinct lines with very specific wavelength values. And there are different patterns for different elements. Here I show hydrogen, here's neon. If you put mercury vapor in there, you get a different pattern. You put sodium vapor in there, you get a different pattern. Those are different lights that you might see in the world around you. Now, within this hydrogen one here, mathematicians of the day noted that it seemed like you could explain this pattern, describe this pattern with a simple equation. Simple meaning it involved the square of these integer values. Mathematicians said, okay, I can sort of explain how these lines look like they're getting closer and closer together in terms of the frequency by just using an expression like this. Now, this is a mathematician. I don't want to put down mathematicians. They're brilliant. I got a good friend who's a mathematician, but they're not providing any physical meaning for this. They're just saying, oh, this is a cool pattern to it. But we're going to use that information and see, well, what is the physical meaning? So what Bohr does is he combines several different ideas. He combines the nuclear model that Rutherford had proposed with the line spectrum and with the idea that energy was quantized. So Bohr, in a way, he started working with Rutherford. He started working with Thomson. J.J. Thomson. They didn't get along. So then he moved on and he started working with Rutherford. He's a postdoc there. He brings together these different ideas. We saw the nuclear model back in chapter 2. We just saw at the start of chapter 6, the idea of quantized energy and photons. And we're adding in the idea of the line spectrum. Bohr brings all of these together for what he thinks a hydrogen atom is like. He thinks that a hydrogen atom is going to be built on these particular features. He is going to say that the electron can be found only in certain distances away from the nucleus. Only certain radii are allowed. An electron is not stuck in one of those orbits, however. It is going to be stable in the one that has the lowest energy, and it could move to another one when it interacts with a photon. It can move to another one, but that movement, if it's going from one energy state to another, it's going to be quantized. It's going to come back to this expression, E equals h nu. These are going to be the ideas that Bohr uses when he constructs what he thinks a hydrogen atom looks like. And I'm going to leave us here, okay? What I'd like you to do next time, I don't have it in a pre-class video, but it's going to be really beneficial. Please read about Bohr's model in the e-text. Please read about that. It's in section, I think, 6.3. And then I'm going to pick up that in our very next class. Once again, we got some really deep ideas that we're right on the cusp of. I really enjoy sharing ideas with you. Thanks a lot for your attention, and I'll hang around if you got questions.
Hi, I had a question about calorimetry. For the coffee cup one, if we're trying to find the specific heat, we're gonna use if we're trying to find the change in enthalpy, we're gonna add the mass of both the water and the system, right?
A key question within that is something to look for is that when you add your substance to the water, look to see, does it dissolve and become aqueous, or does it just stay a solid in there? Because what's changing is the solution. If I add a chunk of gold to it and the gold doesn't dissolve, then I'm only going to be using the mass for what has what the actual liquid solution is. So when we add like a salt to it and it dissolves, yeah, we use the total mass. If I add a metal object to it and it doesn't dissolve, then I would just be using the mass for the water.
Okay. And then, okay, so if it's like a normal what is it called? A calorimeter?
Yeah, calorimeter?
Yeah, if it's not like a coffee cup one and it has separate chambers, then you'd always separate the masses. You want to add them together, I mean.
Good question. Yeah, good question. The reason why I say good question, I see what you're saying, because we had like the depiction for that, right? It had one chamber and then another. Usually for that kind that you're describing right there, those are set up not with a specific heat, but instead a heat capacity is given for the entire object. Those usually don't have a mass value. They have a certain saying, here is the heat capacity for this object. So in those, you don't have to worry about determining the mass.
Okay. And then for one of the examples, this lecture says to predict the sign of change in enthalpy. And one of them is sodium turns into a sodium cation and electron. Is that going to be a decrease in enthalpy or an increase in enthalpy because it's breaking a bond?
I like exactly where you went to. I think what they're trying to say is, okay, let's compare the cation and anion stuck together. Okay, now we can add energy and separate them apart. So the separated apart has a higher enthalpy value.
Okay. And last question is, for standard enthalpy of formation, is the reactants, are they always going to be also in their standard elemental form, or?
Yeah. So within that one, you will have the product, and the product could be, that's usually, the product within that's usually our more complex thing. Maybe it's glucose, maybe it's carbon dioxide, whatever. The reactants then, those are always going to be the parts that we use to get the atoms that we need to make that more complex substance. So the reactants, those are always going to be the elements then as we find them in their standard state. So the reactants will always be things like the H2 gas, the O2 gas, carbon graphite. Those are always going to be what the reactants are.
So you'll never have something like H2O in the reactant?
I can't have H2O as a reactant for that, because I need to just have, in a way, the purest way, the simplest way I can get hydrogen atoms and oxygen atoms, I can't have that being found in a molecule itself.
Okay. I have a question about variables. So I understand in one of our equations that C equals lambda V, that's the speed of light, equals wavelength times frequency. And then in Planck's constant, E equals H times V, E is energy, and V is frequency, right? But then I know like the value of H being 6.626 times 10 to the negative 34, but what is H?
Okay, so a couple things. So you're right within your other expressions. The only thing I change is I can't get a good font for it. So the frequency within that, it looks like a V, but it's called nu, N-U. Okay, so it's Greek letter within that. So if you hear me say lambda nu, I'm talking about the symbol that looks like a V. Okay. So that would be that one. So that, yeah, and you're absolutely right about the units. So when I look at E equals H nu, E is the energy, nu is going to be the frequency. And so if my energy ends up being in joules, that's why Planck's constant has units involving joules and seconds, because the seconds need to cancel the frequency term. So I'm going to be left then with the joule amount. So that the question is, so 6.626 times 10 to the negative 34 joule seconds. What is that? What that's describing now, and that's sort of his novelty, what's unusual. He is saying that, okay, that frequency that you have, sort of the smallest amount of energy that can correspond to that, that's what Planck's constant is. That particular frequency, it's not like it can have a smaller amount of energy. For a given frequency, let's say the frequency is describing blue light. What is the smallest amount of energy you can have in blue with that blue light? Well, you look at what its frequency is, and then Planck's constant is like a scaling factor. It tells you the smallest amount of energy that you could have. A piece of blue light, how much energy would it have? That's what Planck's constant is telling us.
Oh, okay. I was thinking like, you know how the speed of light is 3.0 times 10 to the 8. I thought that like that other number or h would have been like something else, or called something else, if that makes sense.
Yep. No, so Planck's constant, in a way, if you think about that idea of a staircase being quantized, Planck's constant is sort of telling you, well, how high is a stair? What would be the smallest step size you could possibly have? And that's what Planck's constant is.
Okay, thank you.
Yep.
If we're using Planck's constant, are we always going to have to represent, like if they give us the energy, are we always going to have to convert it into joules?
Yeah, I think
Like
what that will be
kilojoules or
either Planck's constant. I always get into joules for that. A lot of times in chemistry, if we're looking at bond enthalpy and the like, the units on that oftentimes are like kilojoules per mole, because that gets us to a scaling that has, you know, reasonably sized whole numbers. But notice what we've done. We've had to convert from joules to kilojoules. And more importantly, we've got like a whole mole's worth of them then.
Mhm.
So that's why we see this really dramatic difference if we're talking about the energy associated with just one bond versus an energy when we're looking at a whole mole's worth. But yeah, Planck's constant, I always, whatever I am looking at, I get it into joules, and because I'm always going to be using Planck's constant as joule seconds. I
Mhm.
guess I could convert that to kilojoules or something, but I never do it that way. I always just keep that as is.
Okay, and then the units for frequency is what, 1/seconds or something? Is that?
Exactly. Yep. 1/seconds.
Okay. And then I don't quite understand, what is how did the photoelectric effect, why does that mean that photons act like a particle?
Yeah, great question. So I went quick over that part. One way to understand it within that is that the fact that you needed to have a particular threshold amount of energy in order to cause the electron to be ejected. It behaves as if the light that's coming in, it doesn't get divided up amongst multiple electrons. It's not like the energy that you have coming in and is going to the entire metal surface. It acts as if the light coming in is being transferred only with one specific electron.
Okay,
Part of the
so
feature of that is that they thought that, well, you know, if let's say I keep shining the light on, and, you know, eventually it should add up to enough energy so that I could eject electrons. What if I just added a small amount, but I did it for a long time? Shouldn't it eventually add up to be enough? It never happens like that. If it doesn't have the threshold value to get the electron ejected, you can let it shine all day, all week. It never adds up like that. It's behaving as if it has to be transferred as if it's a particle from the light to a single electron. It can't be divided up, but if it can do that, then they find that it's being ejected right away. So I didn't go into the details that much, but some of the characteristics are, well, why do electrons get ejected right from the start rather than having to build up? And why does it require this threshold value instead of somehow being able to divide it?
okay, and for each new electron that's ejected, you need to reach a higher threshold?
No, I would
Just
say that
photon.
I would say that once I reach the value that's sufficient to eject electrons, I can stay at that particular value and I can keep ejecting electrons. I can keep having electrons in the metal that will be able to take the energy of the photon and be ejected at that point. I don't have to keep ramping it up higher and higher.
Okay, so it's just the threshold of the energy of each individual photon.
Yeah, and I would say that the threshold, that's a characteristic of the metal itself. Sodium has a different threshold value than gold, than tin.
So can you reach the threshold by increasing the intensity too?
No, you cannot. Good question. You cannot. So when you're in a way, what happens when you increase the intensity, when you increase the brightness, that's as if you're sending more photons at the surface. But sending more photons at the surface won't do anything unless they have sufficient energy to remove the electron, unless they have the correct color, unless they have high enough frequency. It doesn't matter how many you send at the surface. You need to have them above the threshold value for that particular metal. And then once you do, they can be ejected. Once you do, if you make the light brighter, if you have more photons directed, then you can have more and more photons, more and more electrons being ejected. But in a way, that's what was novel within this one. It wasn't like you could just keep taking it brighter and brighter. Brighter and brighter means more and more photons. Crucially, the photon had to have a sufficient frequency. Other than that, it wasn't going to eject any.
Okay, that makes sense. And then, what does it mean for a particle to have like a wavelength, or does that not apply to the particle behavior of the photon?
So your question is, what does it mean if we're saying that something has, a particle has characteristics of a wave within that? Okay, one way, we're going to look more at the idea within that. But you can imagine it this way. Let's say if you've seen sort of a sketch showing something has a wavelength where it's going up and down, up and down, up and down. Okay. Now take that same wavelength, right? That same sort of mental picture and say, okay, that's describing a wave. Now, when we're trying to think of it perhaps as being a photon, let's view it not as being continuous, where it's going all the way across your paper, but you're just looking at one little segment of that. You're looking at a smaller portion of that. So instead of having it go up and down like a wave an infinite number of times, you're looking at a smaller packet of that. Sometimes they call that a wave packet. Okay. You're looking at a smaller part. And so it could have the same wavelength of red light, but it's not continuous like red light. Instead, it's coming in the smallest piece of red light, if you want to think about it that way.
Okay, that makes sense. Thank you.
I have a quick question understanding standard enthalpy of formation. So would you mind going back to the slide that looked at Hess's law and standard enthalpy? So in my notes, I wrote down that the basic format of a standard enthalpy equation is the products are the elements in standard state, and that yields, I'm sorry, I messed that up, reactants of elements in standard state, and that yields a product that is a compound in 1 mole standard state. But in the Hess's law example, it looks like there are 2 products instead of just 1. And I don't understand how there's 5 moles of O2 when I thought standard enthalpy could only be 1 mole.
Got it. So what they're doing within here, so first of all, within the Hess's law part, they're trying to show that, okay, if we use this and try to connect it to what we had practiced a little bit with Hess's law, we could say that this equation right here, this is our target one that we're trying to get a delta H for.
Okay.
And from this one, what kind of equations could we use and combine to get to that? So what it's trying to do is to say, okay, these at the bottom, if we manipulate those, we can turn them around to get to what our target one is. So they're trying to show in this region, this is like our Hess's law. We're going to keep this equation, this first one, as is. The second one right here, we're going to manipulate it. We're going to change the coefficients. We're going to change this. So what they're trying to show is on this left-hand side, they're working through how we can combine equations to get to our final value. Now, if we look more closely, what are they combining? This first one right here, if you reverse that, that would have been the standard enthalpy of formation. You would have been starting out with carbon graphite and H2 to get C3H8. They've taken the standard enthalpy of formation for that and flipped it around. The second one right here, that looks like the standard enthalpy of formation, but they've tripled the coefficients. Why did they triple the coefficients? Because they're seeing what do they need based on Hess's law. This last one right here, it looks like a standard enthalpy of formation, but instead of having 1 mole of product, they have 4. Why do they have 4? They scaled up the coefficients because they want to make it work, again, back to Hess's law part. So what they're doing is they're starting with the initial standard enthalpy of formation ones. But then, like Hess's law, they're manipulating them in different ways. They're reversing them. They're changing the coefficients to scale it up. That's what their plan is.
Okay, I think I just misunderstood because I thought that's the answer that they were getting, like they were trying to find the standard enthalpy. And I was like, that's not standard enthalpy. So they're just using standard enthalpy in this overall equation, but like that, they're not trying to get the standard enthalpy in this.
They're using it. And I think more importantly than using it, they're using it to show that you can get to a very simplified case. You can get to a simplified one. So instead of going through Hess's law and using all of the provided ones, you can just use the standard enthalpy values for the products minus the reactants. This right here summarizes having done all of the Hess's law part. So, I've never used those equations and shown that with Hess's law, yeah, it really works. I instead just say, oh, you're going to give me values in a table. I can just use those values in a table. I can just use those because this is summarizing the process of going from the reactants, getting to the atoms, and then bringing them together.
Okay. Okay, so basically, but still like the standard enthalpy is just like a piece of what you can use to solve more to solve the enthalpy of a more, let's say, complex equation.
You got it. It's just just like we have values for the bond enthalpy, the energy of the bonds, and we can think about, well, what does it mean to take those apart and put them back together? In this case, we have the same thing. We're taking them apart, but instead of worrying about breaking bonds and stuff, we're taking apart to get to the elements, and then we're putting them back together. It's like you've got like Legos, it's like you got all your Legos put together and they make some object. I don't know. What let's say we made a castle.
Okay.
I don't know. Okay. We got all of our Legos, different colors like that. And we ask, oh, what would it mean to take these all apart and make a pile that's red, yellow, blue? Let's take them apart and get all of our piles. Oh, now let's put them together and make something new. Let's make an airplane. So what we do is we take them and we're conceptually taking them apart to get to the atoms and then putting them back together.
Got it. Okay. All right, cool. Thank you.
Yep.
For average bond enthalpies, and using that to estimate the change in enthalpy for a reaction, does it matter if the reactants and products change state?
Yes and no. All right. The no part of it, you will never have to be asked to know the full answer. The full answer is that all of those values as they're written, those are the average values when the things are as gases. Okay. So if you want to be legally correct and use the data properly, that will be useful when you're looking at reactions where the reactants and products are gases. If you were to do that same one, you couldn't, for example, use it if you had liquids. You couldn't use it quite if you had like a solid, a big chunk of something. So legally, it only works if you're looking at gases. But that's not a component that's not mentioned in our text. And so I know that that won't be something that like is intended to trick you or something. So you can just use it, but legally it only works for gases.
Okay, thank you.